Hello, my name is Kennedy Taylor, and the molecule that I decided to study for my project is benzethonium chloride. And some other common scientific names for this include hyamine, quattrochlor, femoral chloride, and femeride. And some common brand names that this molecule is also found in includes neosporin, Purell, and Tannic, which is kind of used for cold sores or any other cold sores that are related to, I'd say, the herpes simplex chain. So this can be used as a topical cream for any open cuts, open wounds, or anything related to that. So benzethonium chloride has many antimicrobial agents and also has disinfecting properties. And this can be used for antiseptic purposes as well. And going into becoming a dental hygienist, I was initially drawn to this molecule because throughout my career as a dental hygienist, I'm going to be disinfecting multiple times throughout the day, and through each patient and every day we are using multiple types and multiple brands of disinfecting agents, and it'll be interesting for me to know how exactly these agents are breaking down these microbacterial forms on all surfaces that we touch and that our patients touch as well. So I was initially drawn to this knowing that I'm a healthcare professional and I will be disinfecting every day. So we're going to begin, and we're going to go ahead and start breaking down the structure. And we can see within the molecular formula that there are 27 total carbons. So we can see that right here. So if we go ahead and count out our carbons within this skeletal structure, we can see that carbons are going to be made where any of the two bonds meet. So basically any points that we see or any ends of lines. So if we go ahead and count these out, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. So we can go ahead and see that our skeletal structure, the amount of carbons, matches the carbon count within our molecular formula. So if we then move on to our hydrogen count, we can see it is a little bit higher. We have 42 hydrogens total. So I will be demonstrating how to identify hydrogens. I'm not going to do all of them, but we can go ahead and start here. So we know that carbon can make 4 bonds. So here we can see that carbon is making 3 bonds to this one carbon. So that means that there's only going to be 1 hydrogen. So the 1 hydrogen plus the 3 other bonds means that carbon made all 4 bonds, and that meets that. So same thing around this whole ring is carbon's going to make 1 bond to hydrogen. Except for when we get right here, carbon's actually already made 4 bonds. So there's not going to be any other additional hydrogens that are going to be bonded to that carbon. But here we can see that carbon only made 2 bonds, so that means we're going to need 2 hydrogen. And down here, carbon only made 1 bond, so that means we're going to need 3 hydrogen. So if we go along this whole skeletal structure, we should come up with 42 hydrogens total. And that's how we find those. So if we go on, we can check to be sure that we have everything that we need within the skeletal structure. So for the Cl, the chlorine, we can see down here. And then for the N, nitrogen, we can see right here. And then for the oxygen, we have to make sure that there's 2, as it says O2 within the molecular formula. So we can see 1 here, and then 1 here. So our skeletal structure does match up with our molecular formula. So next we can point out our functional groups. So one thing that stands out to me initially is these rings that we have. And within the rings, there are 3 alkene groups, or 3 double bonds being made that are in a ring structure. So we know initially that this is going to be a functional group, and it's going to be called an aromatic ring. And if we keep going along this chain, we can see that there is another aromatic ring made with 3 alkene groups as well. Put R there. Okay. And then here, something else that sticks out to me are also these oxygen groups. And if we circle them, we can see that oxygen is bonded to 2 carbons. So if we think about that, we know that those functional groups, those are going to be called ethers. So there are 2 ethers as well. And then if we go over here, we can see that we have this nitrogen, but it's actually bonded to 4 carbons. And we've looked at primary amines, secondary amines, and tertiary amines, but this would actually be called a quaternary ammonium ion. And we know that because quaternary means 4, so there are 4 total carbons bonded to this one nitrogen. But something else that stuck out to me was that we have this chloride atom down here, and we know that it's negative because IDE means that it's going to be negative. And we also have this positive charge on this ammonium ion. So if we put those two together, we know that this is an ammonium ion, but we also know that this is an ion that is found in salt, and it's also an anion. So this is a cation, meaning that it lost 1 electron, and then this gained 1 electron, making it an anion. But if we put those together, we get a quaternary ammonium salt ion. So both of these together make that ion, and then we know that benzethonium chloride in general will be an ammonium chloride derivative, because we know that those two come together and they make that salt ion initially. So that will be quaternary ammonium ion, and then bonded to that Cl makes it quaternary ammonium salt ion. So if we go ahead and piece it all together, benzy means that there are aromatic rings, and we could see here that there were 2 aromatic rings. And then thonium chloride means that it's going to be an ammonium chloride kind of derivative, like I said, and then the IDE means that it's going to be a negative ion. So if we piece that all together, that is the broken down version of benzethonium chloride and its skeletal structure, and also a new functional group that we may have not learned about yet, but I'm hoping to learn about it soon. Thank you.